don't have anything quite this complicated on your test though. But if you did have something a little bit simpler, if you can answer the big question, you can definitely answer the small question. So the question says, write the converse of the rectangle diagonals conjecture. Is it true? And prove it, or show a counterexample. Well, first we got to figure out what is the converse. So the rectangle conjecture stated that if it's a rectangle, then the diagonals would be congruent and bisect each other. So the converse is, if the diagonals of a quadrilateral are congruent and bisect each other, then the quadrilateral is a rectangle. So that's the converse, and now we want to prove if it's true or not. So what I want you to do is on your paper, so in your notes that you're taking, wow, maybe not that one. We'll erase all of this. Yes. I want you to draw a quadrilateral. That's going to be even worse than it was before. Although, and let's call it AB, CD. Let's draw two diagonals, and the point of intersection we'll just label E. So when you're creating an example, you can choose any example you want. And the given information, all right, is that we have quadrilateral ABCD, with, because we want to say that AC is congruent to BD, and they bisect each other. That's the information we're given. Is that enough to say that this is a rectangle? Okay. Now I'm going to talk you through the proof. It takes me too long to write down step by step what's going on. I will write down the information, but I'm going to verbally give you what the proof of it was. And I'm also going to change what color ink I'm using to make it a little bit easier to see, hopefully. Maybe a change of color. Hopefully easier to see. Okay. So we've been given the information, and we want to see, is this a rectangle? Well, if they bisect each other, that means AE is congruent to EC. So AE is congruent to EC. All right? And DE is congruent to ED. That's what a bisector does. It makes one segment into two equal segments. All right? Angle AEB is congruent to angle CED, because they're vertical angles. And I'm going to talk about a couple of different triangles. So I'm going to mention the other vertical angles as well. Of course, angle BEC, and it's congruent to AEB. And that's because they're vertical angles. Okay? Well, now we have two sets of triangles that are congruent to each other. We have triangle AEB congruent to triangle CED because of side angle side, and because of that same reason, we have triangle BEC congruent to triangle AED. So because of side angle side. Now here's where it can get pretty confusing. Let's add in some numbers to make the letters a little bit easier. on our angles. We're going to go through and number all of our angles. Okay, so we know that AC and BD are congruent to each other, so really all four sides that we mentioned in this step, right here, all four sides are congruent to each other. So really AE is congruent to EC, is congruent to DE, is congruent to EB. They're all equal to each other. So that means we really have four isosceles triangles in here. So that tells me that angle 1 is congruent to angle 2, and angle 5, and angle 6. So angle 1 and angle 2 are congruent to each other because they're isosceles triangles. Angle 5 and angle 6 are congruent to each other because it's an isosceles triangle. And then because AEB is congruent to CED, all of those angles are congruent to each other because of CPCTC. Corresponding parts of congruent triangles are congruent. Of course, correspondingly to that, then we have angle 3 is congruent to angle 4 because of isosceles triangles conjunctures, meaning also angle 7 is congruent to angle 8 because of the isosceles triangle conjecture, but because of corresponding parts of congruent triangles are congruent, those angles are also congruent to each other. So I have two sets of congruent angles being congruent to each other. Okay, phew, that's a lot going on there. Now, let's take the measure of angle DAB. If I wanted to get the measure of DAB, I would add measure of angle 1 plus the measure of angle 8. Well, because of addition properties, if I take out the measure of angle 1 and put in the measure of angle 2, and take out the measure of angle 8 and put in the measure of angle 3, then I would get ABC. And if I were to take out 3 and, take out angle 2 and put in angle 3 or 5, so if I put in this list, and I want to match it up with angle 4, then I have the measure of BCD. And if I want to say measure of angle 6 plus measure of angle 7, that's going to be CDA. So mixing and matching all of these parts, because they are congruent to each other and we're using addition properties, I can prove that the measure of angle DAB is congruent to the measure of angle ABC, which is congruent to the measure of angle BCD, which is then congruent to the measure of angle CDA. So that means all four angles are congruent to each other, which makes, I'll clear this off so that we can see it, so hopefully go back a second and pause it to copy that down if you need to. But now we have proven that all four angles are congruent to each other, so that means the quadrilateral is equal angular. So we proved that this angle, this angle, this angle, and this angle were all congruent to each other, so making it equal angular. And then let's draw our diagonals again. And we had angle 1, angle 5 here, and we had angle 8. Actually, I don't want angle 8. Angle 7 and angle 3 were the ones I'm looking at. So if I have angle 1 is congruent to angle 5, well, we already proved that way back in the beginning anyhow, but we can also say, because of the converse of the alternate interior angles conjecture, then if these angles are congruent, which we proved in the previous step, then that means side AD is parallel to side BC. And the same thing, if angle 3 is congruent to angle 7, which we proved in the previous slide, then AB, oops, I get my sides mixed up. AB, this should be AB and CD. Then this would be AD and congruent to BC. And again, because of the alternate interior conjecture converse. So if alternate interior angles are congruent, then the lines are parallel. So now I have opposite sides are parallel. So I have an equal angular. So an equal angular parallelogram, which is the definition of a rectangle. So we have proven that yes, this is a rectangle, so the converse of the rectangle diagonals conjecture is true. Now that's a lot to go through. You may take a couple of listens, a couple of viewings of this video to fully comprehend what all happened. Pause when necessary to understand it. And if you have questions, of course, come and see me.